Now let's read this problem together. So this is a very typical transportation problem where this company, Tropic Cousin, is trying to ship their citrus stored at those three groves in Mandora, Eustis, and Clermont to three processing plants in Ocala, Orlando, and Leesburg. Okay, and the problem tells us how many bushels of citrus are there at each of those groves. And they also tells us what's the processing capacity at each of those processing plants. This company contract with the local trucking company to transport those citrus from groves to the plants. And because this trucking company charges a flat rate for every mile that each bushel of citrus must be transported, so this company is trying to minimize the total number of bushel miles. Okay, and they want to determine how many bushels to ship from each grove to each processing plant. This table gives us the distance in miles between each pair of grove and plant. So with this reading of the statement, we know that, again, from the last sentence, we got the decision and the objective. So the decision is to determine how many bushels to ship from each grove to each processing plant. And the objective is to minimize the total number of bushel miles. And this entire paragraph gives us some general information and tells us, okay, 275,000 bushels is available at Mandora. 400,000 is available here, and 300,000 available here. Okay, and we also have some processing capacities at each of those places. Okay, pretty simple and clear information. Now let's go to the next page where I summarize those information here. Let's look at the decision. Okay, decision: how many bushels to ship from each grove to each processing plant. So that means between each pair of the grove and the processing plant, there should be a decision variable that help us to determine how many bushels to ship. And for many problems, doing some analysis and maybe draw some pictures will help us make the analysis clearer. Transportation problems is one of them. And here let's draw the picture. Okay, so we have Mount Dora as one node, which is the grove, and we have Eustis and Clermont. So these are three groves that have different numbers of citrus that need to be shipped out. 300K. And we need to ship them to three plants: Ocala, Orlando, and Leesburg. Okay, and they have some processing capacity too. Okay, 225. Okay, so these are capacity, and these are supplies. And just now we said we need to determine, say, okay, how many bushels to ship from Mandora to Ocala, and how many to ship from Mandora to Orlando, and how many to ship to Leesburg. Okay, so there are three decision variables just to consider how many to ship out from Mandora. Now for Eustis and Clermont, they are the same. We need to determine how many to ship out from these two groves to the three processing plants. So these arrows here represent the decision variables that we're trying to determine. Okay, so and so there are 9 decision variables that we need to determine, and of course we can use x1 through 9 to represent these 4 arrows. But to make it easier for us to define, let's just number those nodes into 1, 2, 3, 4, 5, 6. Okay, so we have 6 nodes, and our decision variables can be x, I, j, represent number of C choose bushels to ship from node I to node J. I equals to be 1, 2, 3, and J equals to be 4, 5, 6. And we've already defined what 1, 2, 3, and 4, 5, 6 node represent using this graph here. Okay, so this is the first time that we use the subscript in defining decision variables. And in fact, using subscript in defining decision variables are very helpful in many situations. And that's something I would like you to learn. Okay, so with the decision variables defined, now let's say, okay, the objective is to minimize the total number of bushel miles. Okay, so if we are shipping x14 unit of citrus bushels from node 1 to 4, and the distance between them is 21 miles, then the bushel miles that occurred on this one route would be 21 times x14. Think about it. Right? Okay, then if we want to get the total bushel miles, then we need to take this entire table, multiply them by their each individual decision variables, and sum them together. Okay, so I'll ask you guys to write this first. Okay, so our objective function is to minimize the total bushel miles. So you don't have to follow me, you can write it yourself. 1, 4 plus x 2, 4 plus oh, sorry, these should be 1. I'm sorry, I used the wrong. x15 okay, x25 plus 22x26 plus 55x34 plus 20x35 plus 25x36. Okay, so this is our objective function. And then constraints. Let's go to our graph. Okay, so we have supplies and capacities. It is pretty maybe easier and more obvious for us to consider the capacities first. So let's look at this. So usually capacity is another keyword that represents a constraint. Okay, so since those processing plants has their individual capacities, that means, for example, for Ocala, all the citrus that shipped to this processing plant should not exceed its processing capacity. Okay, then what are those input? What are those incoming bushels? Okay, so it's this X14, right? The citrus shipped from Mandara, and this X24. Those are the citrus shipped from Eustis, and X34 representing the citrus shipped from Clermont to Ocala. Okay, so in total, that will be X14 plus X24 plus X34 bushels of citrus shipped in Ocala. And this total number should not exceed this 200,000 here. Okay, so let's write this constraint. So the first group of constraint, the capacity constraint. Okay, so X14 plus X24 plus X34, representing the total amount of bushels of citrus shipped to Ocala, should not exceed the processing capacity there at Ocala, which is 200,000. Okay, then with the same logic, we can write constraints for Orlando and Leesburg. Okay, so for Orlando, all the citrus shipped from the 3 groves should not exceed the processing capacity here, which is 600,000. Okay, then X16 plus X26 plus X36, which are the total amount of citrus bushels shipped from the 3 groves to Leesburg, should not exceed the processing capacity here, 225. Okay, so this is the first group of constraints. That's the capacity constraints. Okay, now let's look at the supply constraints. Okay, it's probably pretty natural for you to think, okay, since at Mondore we only have 275,000 bushels of citrus available, we should not ship out more than what we have here. Okay, then we would write, okay, what we ship out would be X14, X15, and X16. Okay, so these all 3 together represent what we ship out from Mondora. So let's write this. X14 plus X15 plus X16 should be less than or equal to the supply there, 275. In the same manner, we can write X24 plus X25 and X26. So these are all the citrus shipped out from the second node, which is Eustis, should not exceed this 400 available there. Then X34 plus X35 plus X36 should not exceed the supply there, 300,000. Okay, so these are the supply constraints. Now with that, they make sense, right? But when you look at the constraints and look at the objective function, think about what will happen when this model is solved. What will happen to the decision variables? We're trying to minimize this decision, minimize this objective function, right? And all of our constraints are less than equal to constraints. So when the problem is solved, what we will get is 0 for all the decision variables. Because if we don't ship out any, we will get a 0 total number of bushel miles, which is the minimum number here, right? But that's not what we want, right? We want to ship this citrus out to those processing plants so they can be processed, and if we can, and with a minimized bushel total miles. Okay. So what should we do to change the model to represent that? So the first thought would be on the supply part, because for the constraint, for the capacity, they have to meet the capacity. Okay, then let's look at supply part. Should we change those signs so that first, when the problem is solved, we don't get just the zeros for our decision variables, and more importantly, it represents more accurately what we want to do, which is we want those citrus to be shipped out. Okay, so changing the signs here to be equal sign will represent that, okay, we want to ship out all the citrus that we have and let them be processed. Okay, but before we change the sign, there's something that we need to consider. Okay, that is whether we have enough capacity to process all those citrus here. So what are our total capacity? What is our total capacity? Let's add this number up. Okay, so that gives us 1025. So that means in total, at these 3 processing plants, we can process 1025 bushels of citrus. Okay, and let's see how many we are shipping out. Add these 3 up. That gives us what? 975,000 bushels of citrus, okay, which is smaller than the total capacity. And this means, okay, if we change those signs to equal sign, that's fine, because we can ship all the 975,000 of citrus out to get processed, and we still have some surplus in the capacity. Okay. So with that analysis, we now know that, okay, we are going to change, sorry, accidentally, oh, and need to change the color of my pen. That's it. Okay, so for the supply constraint, we're going to put equal signs here, so that it represents we're going to ship out all the citrus at these 3 groves, and but for each of those processing plants, the total citrus shipped in should be less than equal to the capacity they have at each of those plants. But remember that before we change this equal sign, what we did is we compared the capacity. So we compared the total capacity with the total supply, and find out that we do have enough total capacity to process the total supply. Okay, now let me ask you, what if I change this total capacity here from 600 to 500? Okay, what should we do to the model? Okay, so here, this one is changed to be 500 instead. Will this model still work? With this change, our total capacity is changed to be 925,000, which is less than the total supply. Okay, so if that is the case, with those equal sign, our problem will be infeasible. Okay, because if we force those three constraints to be equations, there is no way that these three constraints will be satisfied. So we won't find a feasible solution for this problem. Okay, now should we change something to make the model work? So in class, students considered, okay, let's change back those signs to be less than equal to. But if we change those signs to be less than equal to, we run into the same problem as before, which is all the decision variables will be 0 again. Okay. Now what else can we do? Can we do something to this capacity constraint signs here? Okay. Just now, the total capacity is more than what we can process. So we left those to be less than equal to and change those to be equal to. Now, can we change those signs to be equal to? And change these ones to be less than equal to. See if that makes sense. Think about what does that indicate if we change those signs to be equal to. Okay, so when we change those signs to be equal to, what we are saying is that since we don't have enough capacity to process all the supplies, why don't we just use up all the available capacity? Okay, so we set those constraints to be strict equal to constraint to make sure that all the available capacities are used at all three processing plants. Okay, and for these constraints, they have to be less than equal to, because if we set equal to, then the problem won't be able to find a solution. Okay, and we don't ship out more than what we have here. And with the help of these equal signs here, we make sure that only 925,000 citrus bushels of citrus will be shipped out. Okay, so let me change this. So if the capacity, processing capacity, at this second processing place is changed to be 500, then the total capacity and the supply relationship will be this. So total supply is less than the total supply. Then we have to change the signs here to be equal to make sure all the available capacities are used and we don't ship out more than what we have. Okay, and then all the xij's need to be greater than or equal to 0 for all I goes from 1, 2, 3, and the j goes from 4, 5, 6. Okay, so that would be our model. And another way to do this problem when the total capacity is changed is to add a constraint here. I'll put it here. Would be xij equals to be 925. I goes from 1 to 3. J goes from 4 to 6. Let me change the color. And this one will be less than or equal to. Okay, so another way to model this problem would be using these 1, 2, 3 constraints together. Okay, and this way we make sure that the total number of citrus that we ship out equals to be this 925. So equals to be the total processing capacity, and all those constraints can remain to be less than equal to. Okay, and this is the same as what we modeled without this constraint, but set the capacity constraints all to be equal to. So I'll let you think about this and make sense out of it. And one thing I want to note is that for this second method to model, you need to have these three constraints here. Okay, you won't be able to just use this first constraint and this second constraint, because in that case we're not. Oh, sorry, this first and the second, because we have to make sure that the supplies at each of those groves are still less than equal to their individual ones. Okay. Okay, so that's the model for this problem. Some summary. So first, before we decide the decision variables, we actually draw this graph to help us analyze this problem. And we noted this, we numbered those nodes from 1 to 6, which helped us to define our decision variables using subscript. Okay, and we put the supply and the capacity on both sides. Then the decision variables will be using the xij represent the number of bushel of citrus shipped from node I to node j. And the objective function will be to minimize the total number of bushel miles. The constraint, capacity constraint that we defined first. So what we ship out into each processing plant should be less than equal to the processing capacity of that specific processing plant. Then the supply constraint, we compared the total supply and the total capacity, and find out that we do have enough capacity to process all the supplies. So we want to ship out all the supplies by setting equal signs here at this constraint here. And then we add those non-negativity conditions. Okay, so this is the complete model of this problem.